Ryan, can you confirm that you can hear me well?
Yes.
All right. All right, so let's go ahead and get started. My name is Julia Matevosyan. I'm a chief engineer at Energy Systems Integration Group. ESIG also serves in a leadership role with Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated, holistic approach to necessary knowledge, education, and support power system operators across 5 action pillars. Foundation of G-PST is a group of 6 system operators around the globe who are facing high penetration of wind, solar, inverter-based resources sooner than any other operator in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption and support, and open data and tools. ESIG is a lead of Pillar 1, which is research and peer learning, and more information on G-PST can be found on www.globalpst.org. As a leader of Pillar 1, ESIG would like to welcome you to our August monthly webinar. This is a joint webinar between G-PST Pillar 1 and ESIG, and this is a webinar series. This series is in addition to ESIG's regular monthly webinar series, and it focuses on G-PST research agenda and associated topics that are being addressed in Pillar 1. Topics are presented by both founding system operators of G-PST and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in activities of Research Agenda Group and Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of G-PST is also being provided on a monthly basis through National Renewable Energy Lab, or NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on Get Involved tab. Further information on ESIG can be found on www.esig.energy. Next, I would like to go through a few logistical matters before we get started. So first of all, phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For the Q&A, we use Slido platform, so go to slido.com. You need to open the browser window there, go to slido.com and enter ESIG 30 as an event code. So it's ESIG 30. The instructions are also at the bottom of the screen as you're seeing it right now. You'll see a thumbs up button next to each question on Slido, so you can cast your vote and to help prioritize questions that are popular and as they're being submitted. We plan to save about 15 minutes for Q&A at the end and then wrap it up at the, it's not 12 of the hour, but 30 minutes past the hour. An email with link will be provided once video has been posted. We'll also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. So today's webinar is on operating the system towards zero carbon, and it will be sharing experiences from Great Britain power system. The webinar will feature a plethora of experts from National Grid Electricity System Operator, so I'll introduce them one by one. Anthony Johnson, he is focusing on evolution and development of Great Britain grid code. More recently, he was instrumental in development of technical requirements for storage technologies in Great Britain, in addition to chairing European Expert Storage Group. His latest work involves development of technical requirements for grid forming technologies and looking at black start arrangement from embedded generation. Dr. Chao Kang is focusing on DC systems and power electronics, contributing his subject matter expertise in technical strategy and policy development, new technology and innovation, engineering, and asset management. He is also a convener of newly formed SIGR working group focusing on grid forming inverters. Sharok Bailok has a decade of experience in electricity transmission planning and operation. Her role is to identify future operability risks, define system requirements, and enable creation of long-term solutions to operate the system. Dr. Xiaoyao Zhu has 2 decades of transmission system operation and planning and investment experience. His role is set out operability policy for Great Britain's electricity network to enable the net zero operation, specify technical requirements for new technologies, and define future network needs so that market and network owners can invest in right solutions at the right time. And last but not least, Anna Blackwell. She's a product manager focusing on inertia and frequency at National Grid ESO, and she's responsible for delivering new WAMS-based solutions and tools at National Grid ESO control room. So in today's webinar, we will explore challenges of National Grid ESO that they are facing on their path to zero carbon future, and innovative solutions that are being sought and implemented along the way. Okay, so just a short reminder once again to use Slido at slido.com with event code ESIG30 to ask your questions. And without any further ado, let's go ahead and get started. So Tony, I believe you are first, and over to you.
So I am. Thank you very much, everybody. Welcome. So yeah, I'm Tony Johnson, National Grid ESO. Thank you very much for the invitation to join for us to present today, and we're delighted to share our experiences of the grid forming work that we've been doing in GB. Can I firstly ask, can you see the presentation?
No, we still need you to share. There you go.
Okay, is that up? Everyone got that?
Yes, just needed it in presenter mode, and I think you're good.
Okay. How's that? We're good to go.
Thank you.
Right. Yeah, is that good? Right, fantastic. So we've got limited time, so I'm going to rattle through these fairly quickly, but a number of you will be very familiar with this. Obviously, the drive towards renewable generation has resulted in obviously new technologies which are very different to the traditional methods of generating power on transmission systems, which have relied on synchronous generators, which have basically resulted in the drive towards things like wind, wave, solar, batteries, which are all derived from power electronic converters. They are completely different from the performance characteristics that you traditionally get from synchronous generators. And as a consequence of that, that's had a very significant impact on the design and operational characteristics of the transmission system, particularly in respect of things like declining system inertia, declining short circuit in feed. Essentially, what we're starting to find is that, as you can see here, and I won't go through them in detail, but synchronous generators have certain characteristics. In particular, they're frequency and phase dependent. They provide high fault currents. They contribute to system inertia. We don't get those sorts of characteristics from traditional converter controllers, which are basically heavily reliant on phase lock loops. As a consequence of that, that's having huge impact on the design and operational characteristics of the system, to the extent that we're not getting the robustness that we traditionally would have done. The big thing that we're starting to see is we normally secure our system, or we do design and operate our system to the required sort of a thing called the Security and Quality of Supply Standard, which really covers a situation where if we end up saying catering for a double circuit fault, we can basically rest assured that if we get that fault, we can secure the system. If we start to move to a network which is derived largely of asynchronous plant, without any form of what we call grid forming, the magnetic glue, if you like, that holds the system together, with high penetrations of renewable plants, basically the system can no longer guarantee the stability of the network. So for what we would have had traditionally a traditional short circuit, double circuit fault, which results in which we can secure against, is no longer securable, and we start to ask questions: why is that? And it's largely a result of the declining input that we get from synchronous plants. So if you look at the top graph, we can see the instantaneous injection of active power for a phase change, which is an instantaneous injection of active power. The area under the curve is the inertia contributed from the rotating machines. The lower graph is the effect of a number of different controllers on a power electronic converter type solution. And if we did nothing, we just get the dashed horizontal line. And then by changing the converter strategy, we can get a different performance. But the one we're really interested in is the basically the grid forming model, which has got the red line shown in the first instance that's got a high ceiling current. So if we go to the next slide, we produced two documents which are really important, one of which is called the FES, the Future Energy Scenarios, and what that does, that takes a look at the system from now to 2050, and it is against 4 scenarios. What we do is really look at the situation of, you know, high growth, high uptake of new renewables and electrical appliances, or a situation where we've got slow growth and a decline. You know, those technologies aren't taken up so quickly. But in all of them, what we're starting to find is, you know, significant drive towards electrification, uptake of modern devices, power electronic converters, etc., and all of that's starting to have quite a significant impact on the operation of the system. Now, the second element that's important is a thing called the system operability framework, and what that basically does, it looks at these future energy scenarios and asks the question, well, can we operate the system under each of these scenarios out to 2050? And one of the key things we start to see is declining inertia, declining short circuit level, and a whole raft of issues that start to cause some real design and operational challenges going forward. And all of these are documented in these links that are on the slide here. Obviously the slides will be shared, so I won't go through them in detail, but you're welcome to look through them and see the work that's been done. In particular, things like the performance of phase lock loop converters, all of these present really significant challenges to us. So one of the big solutions to try and solve this problem is, well, could we perhaps get converters to behave in more like a synchronous machine? So the work, this is actually the accumulation of about 10 years work, and it really started back in about 2012, 2013, when a number of my colleagues did a range of studies on the GB network, and identified once they started to increase the volume of renewable plants to beyond about 65%, then the system started to really strain to the point, as I've mentioned earlier, that for us, what we would have a securable fault, the system just basically fell apart, and we had real serious problems. So that resulted in some further work which we did in conjunction with a number of universities here in GB. But basically it proposed the idea of having a grid forming capability, which, as I've said, was trying to get the same characteristics from a converter-based plant that we would traditionally get from a synchronous machine. And actually the technology actually goes beyond that. Actually, virtual synchronous machines, or VSM technology, actually goes back to probably the mid-90s, where it was used in the marine industry for ship propulsion systems. But we took a lot of that work and did some further research, and we published some papers in 2016 where we reran those studies we've run in 2012, 2013, but applied a grid forming converter to the plants, and actually found that we could actually get to operating, you know, 99–100% of the system on a grid forming plant. So that sort of set the ball in motion in terms of you know, this is obviously, is this a viable concept? We then did some further work looking at the implementation of the requirements for generators. That was a European directive that was introduced in Europe, and there's a requirement in there for fast fault current injection. And what we looked at there was a method of looking at various aspects of fast fault current injection, one of which was grid forming. At that stage, the industry felt it was a little bit too much too soon. And we said, well, bearing in mind that we've got to implement the European requirements in 2018, we will go for a more conventional approach, but we will then set up a work group, an expert group, to look at the ability for grid forming to universally be used as a, you know, to demonstrate proof of concept. And that was a very important piece of work that basically proved proof of concept. And we had a number of major manufacturers on that work group who were actually doing some work in the background to demonstrate that grid forming could be used and was viable. And then as a result of that, we then started to actually work on the GC0137, which was a form of minimum grid forming specification into the grid code, on the back of that, we'd obviously had some developers through the GC01, through the 2018 expert group, who had actually done some live trials on a real wind farm. We've got one up in Scotland at Salloch. And then also, as part of the work we've done internally within the ESO, we did a live trial with the University of Nottingham for a project, a small-scale converter, to prove the concept. So on the back of that, we developed a grid forming specification into the grid code, which the work group actually comprised of about 40 members from across the world, from developers, manufacturers, consultants, and everywhere else, to develop the grid forming specification, which was done through grid code modification GC0137, which will provide you all the information that you need and the work that was done. And this is really essential for basically demonstrating that we can zero carbon operation of the system by 2025 and beyond. So what the 137 work group aimed to do, provide a high-level overview of grid forming and the transmission system need, to develop a high-level flexible specification which will be non-mandatory. That's important because basically there are some plants out there or some developers that might not wish to participate, and some plants are better at providing grid forming than others. So it would include obviously a technical specification of plant requirements, the submission of data and models, together with the compliance simulation and tests. We also have a piece of work ongoing that we'll be discussing later on today about the stability pathfinder work, which was basically providing, before the GC0137 minimum specification being developed, the stability pathfinder work was looking at long-term interest for stability products. We'll say that will be discussed a little bit later on today. Then we were to put measures so a more detailed work could take place outside of GC0137. So what we've done is that the GC137 work group has developed a high-level specification of a grid forming capability in the grid code. Some of the detail of that, a number of developers were quite keen on saying, well, how would I actually develop a grid forming converter and prove it could meet the requirements? And that is currently being developed through a grid forming best practice guide, which my colleague Dishao will be discussing with you after this presentation. And that's covering things like basic operation, worked examples, simulations, tests, monitoring techniques, etc. And the other piece of work that we're ongoing is, because the grid forming specification, the grid code is not mandatory, the other piece of work we're developing is a stability market. So basically, for people who have got plants that can meet the minimum grid forming capability, it's then developing the market so they can plug into that model going forward, so that we can then obviously operate the system in a safe, secure and economic manner, and utilising the right volume of grid forming capability that we need. And just to re-emphasise that with grid codes, it defines the high-level requirements. It's not actually a full functional detailed specification. Some of that detail is being addressed through the best practice guide. There's quite a lot of information here. I shan't cover it in detail, but basically the key features of the grid forming capability is, obviously we cover the operating range from DC to 1 kilohertz. But the important part is that it should basically represent a voltage source behind a transient impedance. That's currently not provided by PLL-based traditional converters. But the important thing is that each grid forming converter should be capable of providing phase jump power. So it basically it's the instantaneous injection of active power to the network for a phase change. It should contribute to inertia power. So as frequency starts to change, there should be a contribution of active power as a result of the changing frequency, which is actually the system inertia. And then the damping power, there's a contribution that you get to damping. All synchronous machines generally have damper windings, and as there's a change in speed, that results in a small contribution of active power into the network. And in addition, obviously, we require the standard sort of things such as contribution to active and reactive power through independent control, instantaneous response. So you've got instantaneous response to changes in the AC grid without any actions being required to associated control systems. So it's basically an inherent feature of the design of the plant. The ability to change the voltage or phase of grid forming plant's internal voltage source was only at bandwidths below 5 Hertz. That's so as to prevent undue interactions with other generators or plants connected to the network. And obviously the usual things like being able to ride through grid faults and have grid fault ride through and supply fast fault current injection. The option to contribute to Black Start, which we'll see is increasingly important as our traditional Black Start providers are no longer available. And as we've said, that traditionally these services were provided effectively free of charge by synchronous plant. As we move towards more renewable plants, we've got to plug the gap, and that's exactly what we're aiming to do here. But we have to recognise that because these aren't inherent features of converter-based plant, these features will have to be paid for going forwards. This is quite an interesting slide. This is actually from a real system event on the GB system. But what it does, it's showing the real key features for what we want from grid forming. So we get a fault, and the top graph is showing frequency, the bottom graph is showing the basically active power. And it's the bottom graph I want to focus on because this is showing the key components we want from grid forming. Type 1 is basically the active phase jump power. So as soon as you get a disturbance, that causes a phase change, and the phase change causes an instantaneous change in active power, and that's what we call the active phase jump power. And that is probably the most dominant element that we want to concentrate on. Then we have type 2, which is the inertia power. So as the frequency starts to fall, there's a corresponding change in power, and we call that active inertia power. That's type 2. And then type 3 is the active damping power, which I've mentioned earlier. Basically, majority of synchronous generators have damper windings, and as the speed of the machine starts to change, that induces a current to flow in the damper winding, which itself can also produce some active power to the network. It's only small, but nonetheless, it's a contributory factor. And then type 4, what we call the active control-based power, is effectively the normal control action that you get from a governor system. So obviously if a machine's part loaded and the frequency falls, then its power will start to increase, but it is quite slow because of obviously the dynamics of the machine and the drivetrain and the effect of the governor and the steam valve, etc., all operating. And this is just an example of a simulated study to show a 20-degree phase jump followed by a frequency change. The important one really is to look at that bottom right-hand graph, which is showing the power, and pretty much as we have this change, we get the instantaneous rise in active power. In terms of compliance testing and simulation, all plant that we have has to go through a compliance process, and that includes both simulations and site tests. These are catered for in our grid code, and if you look on the left-hand side, then we've got all the tests and simulations we require for any conventional plant, whether it be synchronous generator or power park module or wind farm. So things like reactor capability, voltage control, active power, fault ride-through, etc. We've then got the sites. We've then got the specific tests and simulations we have for grid forming, which would be obviously testing for the phase jump active power, the inertia power, the damping power, and then if we add the conventional set of tests we do with the grid forming tests that we've recently introduced to the grid code, that completes the full set of tests and simulations to be performed by the grid forming plant. In terms of a market, I've said this is a non-mandatory requirement. The overall system requirement would be defined by the system operator, and then we would look at what we've got on the day through what we call the basic plant schedule, which is basically purely looking at demand and generation and how much generation we need to meet demand, and then we have to add the constraints onto that. So things like voltage, thermal, fault tim feed, fault level. We also have to now look at the stability requirements. So we need that on both a national and a regional basis. The national requirement for inertia, the regional basis for short circuit in feed. So we can procure some of that through the stability pathfinder, and we'll be talking more about that later on. And then the grid forming market, which I've mentioned, which is another piece of work we're involved with, is basically looking at how we can then procure, so to secure the system, how we will procure grid forming together with stability pathfinder plus the plant running in a basic plant schedule to secure the network. And then obviously we've got other market arrangements for things like frequency response, fast frequency response. There's an important point to note here that if we've got fast frequency response, it hopefully reduces the amount of storage potentially that a grid forming plant needs. So there's some certain economies that can be made there, and we're still working on the grid forming market as we speak, but it's an important element to try and get the best requirement that you want in the most economic manner. And then very quickly to summarise, I think we're the first country in the world to have introduced a grid forming specification into our grid code. That was approved by a regulator Ofgem in January this year, and it was finally implemented in the grid code in February 2022. It's consistent with the stability pathfinder work. The full work group report, all the information, the tables, etc., all available from that link. It is a mammoth piece of work. You probably need a good half a day to go through it all, but it is well worth a read if you have the time. The expert group is proceeding. Disha will talk more about that in a few minutes. And we're also working with partner organisations as part of a Network Innovation Allowance project to develop a stability market, which I myself am also working on. And we've now got to the second phase of that, but the first part is available for that link there on the website. And in particular, we're very grateful for all of the people who have helped on this piece of work. Without them, it wouldn't have happened. But in particular, we'd like to thank the extensive work of NSTOR, Siemens Gamesa Renewables, and GE. That's it from me. And now I'll hand over to Disha to pick up on the best practice guide. Thank you very much.
And hi, everyone. Greeting from Dechaokong. First of all, can you hear me clearly?
Yes.
We can.
Okay, brilliant. Okay, thanks for the presentation about our GC0137 from my colleague Anthony Johnson. So now I give you a brief introduction of our current grid forming development and this stage of the GB best practice group. Since last summer, I have been leading ESO's further development of the GB grid forming best practice guide in collaboration with comprehensive more than 50 stakeholders in the GB and wider. Initially, all parties in this best practice group co-shaped and agreed with our objectives and terms of reference. Because Tony mentioned, as GC0137 is a high-level technical specification. So we aimed to use this best practice group to capture comments on GC0137 clauses from our external stakeholders and provide necessary guidance and information, filling in any understanding gap for facilitating future grid forming applications within the GB energy markets, such as the analysis method and the complex testing as mentioned by Tony. Additionally, we think it's a really good opportunity to capture good practice in the GB and wider, as the GB its grid forming is still developing and its early stage with a series of technical challenges to be addressed. So we have invited quite a few external speakers from different backgrounds around the world to share their good practice or insight into opportunities, challenges for GB grid forming technological developments in the GB market. Finally, after consulting with comprehensive external stakeholders in this best practice group, if we can identify the strong evidence to improve our grid code following their comments, we will capture these suggestions for further GC0137 modification in this best practice guide. Yes, Tony, please. That's a nice slide. Thank you. Yes, a group of external subject matter experts, including more than 50 people from GB and wider, have been working closely with ESO to co-address technical challenges as arranged for the following 4 subgroups. The subgroup 1 is very important and fundamental. Is about the clear definition of the GB grid forming plant and its functionality. And the second one is about the analysis methods, particularly for complex testing. What would be the most appropriate method for which type of the compliant test? The subgroup 3 is about the modeling requirements for the analysis tools, because it could be for the time domain or friction domain analysis. There could be various modeling requirements. Subgroup 4 could be the complex testing. We try to identify clearly what is the in-scope, unique, compliant task for grid forming ones. If a generic one for grid falling and grid forming, it can be covered by our ESO generic requirements. But for unique ones like active phase jump power, active damping power, and active local power, there could be some examples can be provided in this best practice guide. And for some really challenging topic, we organize some further discussion on it. Thanks, Tony. The next slide. Yes, the subgroup 1 is led by myself and supported by another 14 experts from different backgrounds. And this one is to provide guidance on the definition of the GB grid forming plant, including what is our grid forming synchronous plants and the inverters, how to define the internal voltage source, and the relevant capabilities in line with the GC0137 legal tests. And according to the group's discussion and some surveys from comprehensive stakeholders, all the challenges and comments and concerns like that will be focusing on the definition of the internal voltage source, because according to the requirements, it looks like the virtual impedance haven't been carefully considered for the impedance representation of the IVS. And we organized a group discussion by this July, and many stakeholders provide the strong evidence to show the benefits of the virtual impedance, and we also evaluate some limitations and some other weak points of the virtual impedance as well. Based on that, we have some common agreement that virtual impedance can be introduced with strong evidence from the comprehensive stakeholders. However, the next question is, if we try to introduce virtual impedance, do we need to have the very clear definition of the virtual and the real impedance, or we just regard as the black box? Because after the of the comprehensive discussion, we think from the position of the ESO, even we define clearly for what is virtual or real ones, it's very hard for us to measure it or supervise it from the position of ESO, because this detail for the developers, manufacturers, they could be the white box. However, for us, that could be the black box. In this position, so the equivalent IVS should be defined as a black box rather than a white box. And we just define what's the functionality and the performance and the inputs and the outputs requirements. Yeah, thank you. This is Tony, go to next slide. Thank you. Yeah, subgroup 2 is about the analysis methodology and the relevant tools. As I mentioned, we just provide clear guidance on when time domain and fixed domain tools are required and what are the most appropriate approach to be adopted. And finally, for the second point, because we introduced a new concept for the network frequency perturbation. That could be different from time domain or not fixing well recognized time domain analysis method. That could be a new concept. So that's why we try to provide more details in the guidance. In addition, so we have some other well-established alternative fixed domain analysis methods or tools. So we probably consider another equivalent and alternative tools for the fixed domain analysis. And based on this subgroup discussion, if you go to the next slide, there could be a very high-level summary to say all the appropriate options for a group of complex types of the compliance tests for our requirement. For those options, you don't need to follow all of them. Based on your organization's capability, your experience, and you just select one or two methods to implement that test, and based on that, you can provide the result first to a reasonable result for the compliance purpose. And you can see that definitely the time domain analysis, including the offline or online EMT analysis, could be could be the option for the wider application for the item 1 to 8. But you know, you have so many literature about the pros and cons of EMT as well. So in this way, you can consider together with some another friction domain analysis, like the impedance-based method, because you know in the ESIG's very brilliant grid forming technical report, they have some more information to introduce some capabilities of the impedance-based method, and also you can consider the method NIP as introduced from us in this grid code. Yeah, thank you. It's a nice slide. Yeah, the subgroup 3 is about modeling requirement, but we consider deeper for what would to produce any further guidance on GC0137 as relevant to the model requirements, and also to capture any good practice from some external stakeholders for the test report, testing system, and possible and allowed it. And finally, we try to identify any unique modeling requirements or key characteristics to be represented in the for the GBGF in water plants. Okay. Yes, the next slide, please. Yes, we have great comprehensive discussion about 3 key questions. I just don't want to talk too much about the wording. I just suggest like we cover 2 things. First of all, we try to say that for the GB grid forming in water and the different operation conditions, including the normal conditions and transient conditions, including the large disturbances or fault conditions, do we need to consider some control mode transfer between the grid forming mode and the grid falling mode due to different operation conditions? And the second thing that do you think some existing definitions for grid falling as per different conditions could be still applicable and suitable for the operational condition definition based on the GB grid forming operation conditions? And based on all the comprehensive discussion, we have some key suggestions. First of all, if the power electronic based converter with predefined grid forming mode, we should keep such mode as long as possible rather than transfer to grid falling mode for fast injection of current. So this is a high level agreement. However, the next step, we should consider carefully about how to quantify some values for the operating condition points. So the relevant the clauses should be reviewed and updated if necessary during the second round grid code modification. And to avoid confusion, we can use the normal operation conditions, or currently we just called wastestand mode is for the transient operation mode, instead of the linear and the non-linear modes to reflect operational conditions. Such definition and relevant clauses should be modified during the second round of the GC0137 modification. Yeah, go, Johnny, please to next slide. Yeah, the subgroup 4 is about complex testing that could be very important ones. And we just similarly to subgroup 3 provide further guidance on the GC0137 clauses if we need to make it more clear. And second saying that we try to capture widely from some comments from external stakeholders, try to say based on their simulation result or any suggestions or concerns about our requirements if they have. And finally say based on their comprehensive review of these comments, say do we have any drivers to change any clauses requirements for the GBGF in water plants, such as the phase jump angle withstand of 60 degrees, Yeah, the next slide. Yeah, so we organize several discussions around 3 questions, particularly about active phase jump angle withstand of 60 degree, because according to some stakeholders simulation or some study result, it could be sometimes it could be really hard to achieve such compliance. So we organize clearly for try to make it clear what kind of scenarios can potentially trigger phase angle change up to 60 degree when considering compliance for such active power phase jump under extreme conditions. The second one, that for the extreme condition, do we include the faulty conditions? If we included the faulty conditions, do we think the 3-phase fault can be regarded as the worst one or sufficient? So do we, and question 3, so if it's to evaluate, is it still challenging for GBGF in water to run through a phase jump, even with phase angle change up to 60 degree? So some key suggestions that could be suggested and concluded from the stakeholders say some scenario suggested, but a very rare condition in a very small part of basic grid, not for massive rollout of the grid forming. And the second thing, that for 3-phase symmetric fault, according to our grid code definition, the voltage will dip to 0 during the fault conditions. So in this way, the active power jump power equal to 0, because the voltage equal to 0 is independent from the angle change. So in this way, we, based on evaluation, we think low voltage rise through would cover as the output power, because output power is independent from phase angle jump. But for a symmetric fault, we still need more detailed consideration to evaluate. We still need to consider the phase angle jump up to 60 degree. And the final thing, that based on some evaluation, probably we will think about the phase jump withstand requirement up to 60 degree. Still is such the restricted requirements, and based on the further studies and some further efforts, we will evaluate. Do we need to change that during the second round of the GC0137 stage? Okay, that is the end of my slide. Thanks for listening. And the final thing is about the future plan. So far is there could be multi-stage best practice guide for the draft review, and some comments with intensive interest will be discussed in group meeting around the end of September, and the best practice will be further updated and final issued by end of October after the official approval of the grid code panel. Yeah, that's it all. Thank you.
Hi, thanks, Zhao, and thanks, Tony. So I will be talking about Stability Pathfinder and trying to give you a very brief overview, but please feel free to write as many questions as you want in the Slido. And if you're not able to cover the questions, I'm happy to answer them after the webinar is finished as well. So yeah, so a brief overview of Stability Pathfinder, what it is. So as Tony has mentioned previously, that we have been running Stability Pathfinder project. So Tony, if you go to the next slide, please. So yeah, so as we have been mentioning, that traditionally synchronous generators have provided stability characteristics such as inertia, short circuit in fade, and dynamic reactive power. And as we are moving towards a system where we are getting more renewable generation connected, we are getting more converters connected, and hence we are getting less synchronous plant running in the system to meet the demand. So we do need to find something in order to help with system stability. And the key issue is we need to find something new as a new asset, new build asset solutions. And as Tony has mentioned previously, and that Joe has mentioned about the ongoing work in the GB Grid Code, I think it's just worth mentioning that those work streams are still ongoing, and Stability Pathfinder is something we have been doing in parallel while in the absence of any legal text in the grid code for the grid forming technologies. So what is Stability Pathfinder trying to achieve? Essentially, we're trying to look at different solutions and trying to meet the stability requirements in the GB system in the most cost-effective. And we're comparing market-based solutions with also incorporating transmission owner asset-based solutions as well at the same time. And this is the first time we are looking at providing long-term commercial contracts. So this was the very first thing, or first time we have actually gone down the route of very long-term contracts for ancillary services. And all our pathfinders, included stability, voltage, and constraints pathfinder you may have heard of, are all trying to do learning by doing approach, as you would hear us talk about Stability Pathfinder as well, that we have been trying a new process, learning as we go on, and trying to improve the next phase of the project as we go on as well. Tony, next slide, please. Right, so what exactly are we trying to buy or define in terms of technical system requirements? It's very difficult to define stability in a single figure, but so that's what we have tried to do. I'm sure there will be things we do in the future maybe different than what we have done until now, but in terms of key system studies we have been looking at are essentially looking at voltage and frequency stability of the system. So in terms of frequency, we're focused on inertia being a national figure, obviously, but we have been trying to also look at the regional aspects of inertia if we do have any regional requirement in the future for inertia. Alongside inertia, we have been looking at voltage performance. So what's happening to the voltage behavior in the system during the fault and immediately after the fault in order to focus on what we want to buy in terms of a stability product. So we have been looking at the behavior as a retained voltage during the fault on the GB system. Voltage, faults can last up to 140 milliseconds, so maximum period in the GB grid code that's allowed. We've been looking at what happens to the voltage after the fault is cleared. How fast is the recovery? Is it does the voltage need more support in the interim period when the fault is cleared? Are we seeing any major temporary over voltages on the system? And so understanding what that behavior is helping us define the stability requirement for the Stability Pathfinder work. And alongside that, we have been looking at short circuit ratios. Been trying to incorporate any industry-wide literature available on short circuit ratios. As we have gone on different phases of the Pathfinders, we have improved, and we have been also consulting recently on short circuit ratio implementation in the GB system through our system operability framework consultation as well. So it's the single figure that we are buying as a short circuit level in Stability Pathfinders is reflective of all those things that are in that slide. So it's very difficult to quantify something as broad as stability in a single number, but that's what we have tried to do because we are running a procurement process where we have to be able to value something that is being provided as part of the procurement. Tony, please, next slide. Right, so this is very brief summary. I'm not going to go through everything in detail because a lot of stuff hasn't already been talked about with by Tony and Dachau earlier. So the key technical specification is the key part of the Stability Pathfinder has been defining the technical specification or the technical capability we need from the plant that is able to provide a stability service. And when we started with Stability Pathfinders, we did not have the GC0137 work as it stands now as part of the GB grid code. However, we did have versions of GC0137 drafts. So we have used the GC0137 work as much as possible as part of the Stability Pathfinder specification. However, the Stability Pathfinder specification may be slightly more on top of the GC137 work, or it may be slightly different in terms of wordings and text. However, the work is to ensure that we are as much as aligned with the GB grid forming spec and the grid code. So the key characteristics are, of course, inertia, getting instantaneous fault current, active power change caused by phase angle changes, rock off withstand, fault right through, some compliance requirements, adherence to that, damping power, and other characteristics of the grid forming technologies. It's worth noting that for this Stability Pathfinder work, we have defined separate compliance requirements to ensure that the providers or the prospective tenderers have visibility at the time of the tender what compliance requirements are expected of them. So we already have those documents for the commercial service providers. However, the ongoing work that Dachau has mentioned has been building upon the commercial and compliance requirements for Stability Pathfinder. Yeah, if we go to the next slide, please. Right, so just to give a brief overview of what the tender process looks like for Stability Pathfinder, essentially, we are running a procurement process. So before the procurement starts, we are looking at the system requirements. That's where we do our technical studies, defining what we need in terms of stability in the system, which is a number comprising of inertia and short circuit level. That's how we have defined the stability requirements so far. And then we are ready to run some pre-tender consultations, either through request for information from industry or through a series of consultations. Once we have some feedback from industry on different aspects of the tender, we are able to start the tender process through the launch of an expression of interest. And that's where we are providing more information to the market regarding the technical specification that the assets are being asked for the service, the contract terms, and the how to participate in the timescales for the tender itself. And then there is a tender window where we carry out different webinars, consultations throughout the tender submission as well. And the tender assessment consists of technical assessments as well as commercial assessments. And then there is a tender award. After that, the whole process can easily take 6 to 8 months. So it's a very long process and very time consuming. And also, of course, not just for the National Grid ESO, but also for the participants who are participating in the process. Yeah, Tony, next slide, please. Right, so so far we have run 3 phases of the Stability Pathfinder project. So the first phase was concluded in January 2020, and that's where we had run a very fast tender process over a 2 months time frame, and we were looking for to boost up our inertia levels on a national level. So it was a national-wide tender in the GB system, and essentially our requirement was to boost up our inertia. And we limited the tender to synchronous only solutions, 0 megawatts, or solutions that do not export active power, and just to ensure that we are able to rely on the solutions and they're able to deliver faster in the time frame we were looking for. So in that event, we procured about 12.5 gigawatt seconds of inertia, and the contracts were signed up to 6 years. And this was the first time we signed any long-term contracts for any ancillary service on the system. Stability Phase 2, which is focused on Scotland alone. So it was looking at increasing short circuit level in Scotland and across a few regions of Scotland. So the tender was very specific as to where the solutions were required. And the tender has just concluded in April 2020 this year. And the solutions are going to go live from April 24. And this is the first time in this tender we allowed synchronous and all other technologies to participate. And we had performing converter technologies and hybrid solutions participating in this tender. And in this tender, we have procured short cycle level in Scotland, but of course, we still want to procure Inertia because a grid forming technology will give us Inertia as well. And we have valued in the tender assessment anyone who is able to provide a level of Inertia, and we had targeted 6 gigawatt seconds of Inertia in this tender. And this round of tenders, we have signed contracts for until end of March 2034, so up to 10 years for some providers who are successful. So the third phase, which is still ongoing for Stability Pathfinder, is looking at a different region of the country, which is England, Wales focused, and it's still ongoing. Tender window is open. Tender window is now closed, but the tender results will be announced next few months, and the go live date is expected from 2025. And this is similar to phase 2, except that it's in parts of England, Wales rather than Scotland. And we're just looking at locational boosting of locational short circuit level. And alongside, we are also buying Inertia to top up our national Inertia levels. And for this tender, the contracts would be at the end of March 2035. And just general information for all these contracts, we have been looking at availability payments for providing short circuit level and Inertia. And these are the parameters that are valued in the tender assessment. However, it doesn't mean the technology doesn't have to provide anything else. So the technologies any technology has to ensure they are able to meet all aspects of the grid forming technical specification, not just providing short circuit level and Inertia. It's the short circuit level Inertia that's actually valued in the assessment. However, the first pass is to be able to be technically capable of being grid forming. And there's additional utilization payment for any other reactive power we are using within a settlement period as well. So if I go to the next slide quickly. So this slide just gives you, all of the results are available on our website. So you should be able to go to our website, Stability Pathfinder, and download the tender results. You'll be able to see a lot more information there. And this slide just gives a brief overview of where we are in terms of the number of solutions or the providers that were successful. So Stability Phase 1, we had mainly synchronous compensators because we were limiting the participation to synchronous technologies only being able to operate at 0 megawatts. And in that tender, we had all the successful providers, and their Inertia values are shown there. And most of them are live, and a few of them are still just waiting for some commissioning tests will be live in the next few months. So yeah, it's just helping us with the national Inertia levels. For Phase 2, Stability Phase 2, which was Scotland specific, we have procured some grid forming battery storages as well. So it has been really exciting to see new technologies appearing on the system. But the dates you can see are most of the solutions will start appearing from 2024. So they'll probably be starting connecting and starting their construction programs very soon. Yeah, so it just gives a overview of what the results were for these different tenders we have run so far. So quickly go to the next slide, Tony. So yeah, just quickly recapping that Stability Pathfinder has been a learning by doing process for us. It's the first time we've tried to run something in a long-term tender process, and each process of the tender has been modified as we have gone from Phase 1 to Phase 2 to Phase 3, and there have been a lot of improvements throughout. I've tried to pick up 3 key challenges or key learning points so far. And first of all, the biggest learning or the challenge for us was how to define a tender process for a technology that we do not know how it will behave, which is a grid forming converter technology. So we had to come up with a tender stage where we had to look at or ask for lots of technical simulations from the participants to be able to demonstrate what they can do or what they can't do. So that was a key part of the tender. Similarly, for connections, we had challenges and lots of learning as to how we allow for connections of these new assets. And so has a different approach we have applied in Stability Phase 3. We have tried to reserve base for potential tenderers or successful providers as part of the process as well. And of course, the biggest challenge has also been trying to compare commercial solutions against regulated TO asset solutions. And it's like we're comparing 2 different things. So it's been challenging to understand limitations with this sort of assessment. Quickly, the next slide. yeah, I think I don't have to spend too much time. It's because Tony's already touched upon stability market. There's a lot of information on stability market on the website, link over there. So stability pathfinders have been ad hoc approach. They're not our enduring long-term approach. So we have to look at development of a short-term and a long-term stability market, and long-term stability market could be something that stability pathfinder turns into in the next few years. Yeah, I'll just pass on to Jaya now, just being conscious of the time.
Yeah, thank you, Shuruk. Yeah, good evening, everyone. As Shuruk just mentioned, I mean, through the Stability Pathfinder project, we are buying quite a lot of short circuit level from the system to pop up the system strengths. But there's a fundamental question. So what is the system strength, and what's the right way to measure it? So I just want to briefly talk about some innovation project we're currently doing with Imperial College on this subject. So Tony, if you move to the next one, please. Yeah, I think traditionally, short circuit level is a standard measure of the grid strength to indicate how stable the electricity system is. So that index actually works quite well in the past many years when the system is a synchronous machine dominated system. But when we start to move away from that system to become an inverter IBR dominated system, so there's a question you'd be asked, is that still the right measure or not? I think there's a lot of work has been done in this area, like people proposing alternative ways to the short circuit level, like the available short circuit level, or using some of the sensitivity from the Q against V as a right measure. But there's no indication to say what actually is the right thing to do. So Tony, if you move to the next one, and the next one, please. Yeah, that's just pose a question to say what actually is that short circuit level still a good all-purpose indicator. I can pick up an example from next slides, Tony, if you don't mind. Is that can you go next, guys? I think that Imperial College does or the next one, sorry. Oh yeah, that's the one. Yeah. So if you're picking up this one as an example, when we're looking at typical issues, currently we're facing a lot of the IBR connecting the system. So we would have potentially a control interaction type of oscillation issue, or the harmonic instability issue as well. And one of the effective way of analysis this type of issue is by looking at impedance scan. You're forming a whole system impedance model and looking at the different different oscillation mode and looking at different participation factor as well. As we all know, that control interaction, I mean, the frequency, the oscillation frequency could be quite far away from the fundamental frequency. But when we really looking at short circuit level itself, it's still based on the fundamental frequency. So it's a pose question, I mean, is that the right thing to do or not? And Tony, if you move back one slide. Back one. Yeah, that's great. So this is just the main thing we are trying to do through the Strength to Connect project. The issue is, as I mentioned, the short circuit level has been used as overall one single index to measure the system strengths. And but when we're looking at system issues, they actually have a different type of system issues, whether that a single index still that fit for purpose or not. And we have to looking through this by this project. If we're looking at 4 potential issues in the system, that we could have a voltage regulation problem. So we could have increased the recovery time from the voltage dips, thus retained voltage and voltage recovery issues. And we also have the potential instability of the grid following inverter due to the PIL design issue. Or we could have the operation of the protection issue. So all these issues, I mean, by using the single short circuit level might not be appropriate. So what we're actually going to do is by looking at different measures for the different type of issues, and we are doing the simulation to testing whether that's effective or not. Then based on that, we try to propose a separate, more targeted measure for the different issues. So Tony, if you move to the last one, please. Yeah, next one. Yeah. So the idea is by looking at individual system issues, we might be able to come up with a different index that could be the right index for us to characterize that type of issue. And based on those information, we can then establish the right system requirement based on the different system issues. And we can potentially create a new product we can put onto the market, and all that analysis could be a quite useful input into the stability market we try to develop. So overall, we're trying to review that what the short circuit level is still the right single index for the grid strengths, and we might be able to, or we are looking to investigate is there any other different measures for different type of issues, and those issues could be forming that our new system requirements, or could be forming our new product specification and be part of the input to the stability market. So that's all my slides. I'm going to hand over to Anna to talk about inertia management. Thank you.
So yeah, hello everyone. And you can go on to the next slide, please. In fact, actually, can we go on to 2 slides time? The next one, that's it. So the slides I've just skipped over kind of summarise what everyone's said about how inertia is decreasing on our system. And as a result, it's costing us more to balance the system. But to save time and to leave more time for questions, I'll skip over those in much detail now. As we've mentioned, what's key to a lot of what we're doing is understanding how much inertia is on the system at any one time. When we had lots of conventional plants, traditionally the majority of our inertia came from that sort of bulk generation plants as rotating inertia, so the steam, hydro, gas generation plants. Now we're seeing sort of flywheels come along, and then there is a proportion that comes from sort of the load, rotating machine based load or inverter based resources. Historically, that bulk generation provided the majority of the inertia, and probably sort of 90% of it. And we've historically estimated the amount of inertia on the system by summing up the inertia from the known synchronous machines, and then adding in a percentage based on the demand of the system at any one time. However, as the traditional generation is closing and we get more renewables on the system, that balance is changing, and understanding how much inertia is actually contributed, how much effective inertia is being contributed from load and inverter-based resources is becoming much more important, as it's a much higher percentage of that total inertia. So as a result, we're moving now towards wanting to measure that inertia and having a much clearer view of the forecast of that inertia. And as a result, we have, in the last couple of years, contracted and now implemented 2 brand new, first of their kind inertia measurement systems that have rolled out of various research projects. One was National Grid funded and initiated, and another one came out of European innovation funding. Can we move to the next slide, please, Tony? So both these 2 systems work on looking at basically changes to the frequency as a result of the inertia within the region. If assuming everything else changes, it stays the same. One of the solutions comes from GE Digital and is work based around using PMU devices to look at regional inertia and looking at changes around the boundary flows. And this produces a real-time inertia value for what's currently going on the system, and then also has the capability, using some machine learning technology, to forecast the inertia, in our case up to 24 hours ahead, but actually could be significantly more than that, based on the quality of the input data that you have. So it uses forecasts of demand, forecasts of synchronous generation, and of embedded and renewable generations to be able to pull together that forecast of inertia. And then it also does what's called a T0 forecast, where it runs that same algorithm using live real system data to compare to the real-time calculation, the real-time measurements, and refine its machine learning. We've had this system up and running, but only looking at the Scottish part of the GB network since about October. And we're currently going through some analysis with it. But at the moment, we're seeing very good correlations between our estimate figures and what this is giving out. And we've got good confidence in how it's working. We are looking to roll it out to cover the whole of the GB network as our transmission owner colleagues start rolling out or increase their rollout of PMUs, phase of measurement units, across their networks, because we need those to do a complete boundary measurement before we can actually get the inertia calculations. And they're due to roll those out across their whole networks over the next 3 to 4 years. Tony, can we move on to the next slide, please? Thank you. The other tool that we've got in place is from a company called Reactive Technologies Limited. This uses their dedicated XMU units, which are smaller versions of sort of PMUs, but only looking at frequency, and are generally installed across the lower voltage distribution networks, and works on having a known signal that is put out. So in our case, we've had built a what I think is the largest continuously operating synchronous compensator in the world, that's sitting in the northeast of England, and is continuously putting out a low frequency signal that is then picked up by the XMUs, and they look for distortions in that to measure the inertia. This system has been fully up and running for about the last 6 weeks. And again, we're going through analysing the data from it at the moment to build up confidence in it as a new tool before we start looking at how we implement this into our systems going forward. Can I have the next slide, please? So on the screen here, I've just got some examples of the sorts of data we're getting out of the tools. The left-hand two show data from the GE system. The right-hand graphs are from the reactive system. So in both cases at the top, you've got a plot of inertia. The left-hand one shows in yellow the inertia for the last, I think it's 24 hours with the confidence level, and then the bit in blue is the forecast inertia for the next 24 hours. The red graphs on the right-hand side, the bottom one again is the inertia from the reactive system. These are for different time periods, I should say. And then the graph above it is the largest loss on the system at the time. The GE system also captures frequency data associated with large loss events, and it uses these to calibrate its own calculations. So at the bottom, you can see an example of a large loss of load on the GB system and the impact on the frequency on the left, and the rock-off shown on the right, and the change in the boundary flow that it's monitoring. If you can move on to the next slide, please, Tony. So we're currently assessing, as I said, both these tools. We've made them available to our control room in the last couple of weeks, so they've got them for visibility, but they're not currently using them to make decisions against. And we are carrying out some independent work with an independent third party to assess the accuracy of these tools before we look to start implementing them and then using them to things such as being able to determine how much inertia we need to procure in the future, and also what sort of response tools we need in place. Thank you very much. I think that's the end of our presentation, and we'll move on to questions and Q&A.
Right, thank you so much. So a lot of good information, good tools. So we have about maybe 15 minutes for questions. I'll start with not the most popular question, but I think it's a clarifying one, and it relates to the title of the webinar, so I'll start with that. What does zero carbon option mean for GB Grid? Is it 100% renewable generation?
Yeah, I think I'll just chip in here. My colleagues will probably be able to add a bit to this, but yeah, I mean, I think it picks up on the point that was mentioned right at the beginning, that we ran a study, my colleagues ran a study, identified as soon as they got to above 65% non-synchronous generation, the system started basically collapsing. So for what you'd have as a credible fault that you could secure against, the system fell over. What we can do with grid forming is, bearing in mind that a lot of them are using renewable technologies, what it's basically saying is if you ended up with 100% converter base or IBR resources, you could actually operate the system with 100% of that without running into problems. That's ultimately what we're saying.
I think it's just worth adding that the ESO ambition of operating a zero carbon system in 2025 is essentially reflecting that if the market provided us with a dispatch that is zero carbon dispatch, we don't have to take additional actions, which is cost to the system operator, and we're able to operate the system without taking such action. So it's up to the market to provide us that zero carbon dispatch as well.
Yeah, Sharuk, I'm a little bit familiar with that discussion, so just would it be fair to say you still have a number of nuclear units running, right? So zero carbon would include those nuclear units as well. Yeah. All right, thank you. Let's go to the next question. If inverters are being asked to behave like synchronous machines, is there a concern that the full capability of inverter won't be utilized?
That's an interesting question. The specification we've introduced, as we've talked about, phase jump power, active phase jump power, rock-off response power, and damping power. The important part is that whilst all plants have got to have the capability to provide each component, there's no minimum requirement for each to provide a minimum volume for each. So you might find that a battery's got good storage and therefore can provide good inertia power, good phase jump power, and good damping power. You might, on the other hand, find a wind farm that's probably quite good for contribution of short circuit in feed, but not so good for inertia power. For phase jump power. So what we've been trying to do is that what we really didn't want to do at the outset was to try and have a minimum requirement that everyone had to sort of get to a de minimis level, because obviously that becomes non-competitive, and it's also basically excluding a lot of participants as well. So we said that each plant has to have these three components, but the volume that they produce is entirely down to them, and then they can submit the price that they wish to provide for the operation of that service, and then we will dispatch them based on what we need. So therefore we should be able to achieve what we want at minimum cost without resulting in developers suddenly having to invest put lots of extra gear in, which is expensive, to get to a minimum requirement. So that was the thinking behind the specification.
Right, sounds good. Actually leads well into the next question, which is mine. Is it envisioned that all grid forming capabilities will be procured as a single market product, or are you planning to split into several?
So maybe I'll jump in. So at the moment, we are defining a grid forming specification as a requirement for any potential stability market, and the technology will have to meet that specification. So at the moment, the aim is still to procure as one stability product, incorporating all technical specifications of the grid forming aspects. But again, there is ongoing stability market work, which will inform us if that is the right thing to do, or there is further feedback from industry on we should be doing something different.
Let's go to the next one. I think that refers to, Tony, that table that you had about demonstration of different grid forming capabilities and what kind of tools need to be used for that. And so a question from Deepak, our mass simulation environments can indeed be used to test rock-off based events, but the slide suggests otherwise. Could you kindly provide some insight?
Just trying to understand the question in a bit more detail there. So basically, the studies that we do for modelling, I hope I'm going to answer the right question here, but do correct me if I'm not picking it up correctly. Obviously, for study work, for the system operator, we utilise full RMS-based studies. We can model the whole system, but for more localised stuff, you use EMT type studies, electromagnetic time domain type analysis. That study that I showed to you on the screen was obviously one that we've done for a 20% phase jump and a frequency change as well. The compliance tests, obviously we will do a full suite of tests to demonstrate phase jump power, inertia power and damping power. And we are actually working, so our grid code does include a set of compliance simulations and a set of compliance tests, and the clauses of the code that referred to was covered in the slide. And then further work is being done on that. So Dishao mentioned some of the work that's being done through the best practice guide, which is adding some more detail to that work. But ultimately, what we're looking to do is, this is a very high level. When we go to the grid forming market, the grid code basically requires developers to submit the data associated with their plant. So what the parameters are, the ratings, the phase jump power, the inertia power, the damping power for a particular type of disturbance. We then use the models that we get for simulations to run that, and then we'll do tests on site to demonstrate the tests on site and show an accurate reflection of the simulations and the data they've submitted, which basically results in a pre-qualification. And once that's all been proven, then that means that plant can then be used to be used in anger as part of a stability market product, or indeed as part of the stability pathfinder work that Sharuk has mentioned. I hope that's answered the question. I'm not sure I've fully understood the entire question, but hopefully that's answered it.
Yeah, I think it does, and I think where Deepak is coming from, kind of point he was making in a recent paper that came from EPRI, is that if certain features are included in RMS model that are currently not, then maybe you can use RMS tools for more things than you do it today.
Yeah, so just to add to that point, which I sort of covered for, it is important that you can get some simplifications, because if you're modelling, you know, a system like ours with 300 buses and all the rest of it, you need to get a quick result, and also from the purposes of managing constraints. So ultimately, as this factors down, there will be a need to calculate constraints at regional levels for both, you know, for short circuit in feed to secure those parts of the network, but also for inertia as well. You want to do that, be able to do that fairly quickly as conditions change. So an RS model is very beneficial for that purpose. EMT DC will give you a much more accurate model, but it takes a lot of time to do that. And obviously having simplifications is a very valid and important tool in managing that process. And I think Dishao, as part of the best practice group, is doing some of that work as well.
All right, let's go to the next question. I think it's maybe Sharuk mentioned that what is, and the question is to her then, what is regional consideration of inertia?
Yeah, so I think of course, the region, we are looking at inertia at a national figure when we are doing operational planning, and in, of course, next few years, that's what we're looking for. But going forward, or in sometimes the events we see in the system with faults, we see large fluctuation between different regions of the country in terms of the rock-off limits we see. So going forward, so far, it's not been an issue. We don't think one region is an issue compared to another region, but going forward, we need to watch it and understand if we have to worry about regional inertia or regional rock-off levels going forward. But then it's a lot of this work is going to be informed by Anna's presentation, where she talks about inertia monitoring tools, because they are going to help us understand if there is variation of inertia between different regions, and should we be doing something different than just looking at a national figure.
Thank you. Do all wind and solar farms will be required to have grid forming capabilities?
No. Yeah, it's a non-mandatory requirement, and basically what we want to do is basically there'll be a market, and then we encourage providers to come to it now, whether they're wind, wave, solar, even smart loads, electric vehicles. If they've got the capability and they offer the right price, then obviously they've got an opportunity to go into the market. But no, the answer is it's a non-mandatory requirement. So therefore, there's not a requirement for all plants to provide grid forming.
So the next question is with respect to slide 3, and I think you had this bullet point there that synchronous generators are providing multiples of per units of fault current. So the question is, have you asked PLL-based IBRs to provide high short circuit current, and if so, have OEMs said they cannot provide this current?
Yeah, they can do. This is something that we looked at as part of the implementation of the requirements for generators in Europe. And we came up actually with 3 options. We came up with grid forming. We came up with grid forming. We came up with conventional converter, which is PLL with a high fault in feed, high fault current, high ceiling, and the same again as just a PLL with a fault current in feed, but with a lower setup 1 per unit. And we said that we're happy with all 3 options, but if they went for the PLL option, we would look to set up a grid forming. So the answer is that they can contribute to high fault currents, but they can be a little bit sluggish in speed. It is possible to use PLLs. They do actually produce something equivalent to grid forming, but one of the issues is that the impedance between the internal voltage source and the connection is actually in a grid following converter is actually set quite high to almost infinite. So the effect of the phase jump power in that situation becomes very limited, and that's the one problem that we have.
Mm-hmm. The next question is, what is best time frame for procurement of grid farming services? 5 minutes, hours, days, years, contracts, or spot markets?
So I think, so for pathfinders, obviously we will look at long-term contracts up to 10 years. So we are procuring services 5-6 years ahead of time. The stability market work that we have mentioned that's currently ongoing is looking at short-term markets for day ahead or year ahead. We haven't yet, that work needs to conclude to advise if there is a value in year ahead or not, but certainly they're looking at day ahead as an opportunity for short-term market.
Mm-hmm. And the time resolution, are you looking hourly or less than an hour?
So it will be a settlement period, which is the resolution for all our services, 30 minutes, that is.
Yeah.
All right, thank you. All right, next question is National Grid ESO recommending any particular positive sequence model for simulating grid forming converters? What type of model, in parentheses generic, is being used in the planning studies?
I don't want to put D-Shell on the spot here. I don't know if that's something that's being talked about as part of the best practice group. If D-Shell's still on the call, I don't know if he is.
I'm not sure whether D-Shell is on the call or not. I mean, so
okay.
currently, yeah. I mean, the studies we done by the improvement system stability is some of the in-house model we developed by ourselves, the IMS model we developed by ourselves. We're not aware of currently that the generic sort of grid forming model available, but once we receive the submission from the manufacturers, that's the one we tend to use them in our system to looking at particular impact to the rest of the system.
Mm-hmm. Yeah, and to that end, I can say that WEC is currently working on developing a generic model, and EPRI is working on developing one, so it's coming up. Stay tuned. Right. The next question is as IBRs take over and there are fewer rotating generators, does rigid frequency control becomes less important for stability, for example, for under frequency load shed schemes? I guess the question is, does it even make sense to keep rigid frequency if you have all IBR system?
That's an interesting question, because whilst you've got frequency and it's got to be set at 50 hertz, if you're still back to the same old conundrum of you've got to manage generation and demand minute by minute, second by second. If there's more generation, there is demand, frequency goes up. If there's more demand than generation, frequency goes down. So in the event that we end up with a deficit of generation, frequency will dive, and therefore to protect the system, which is the last bit before effectively the things start to go horribly wrong, then low frequency demand disconnection would be a welcome tool. But I'm happy for others to add to that.
Yeah, I think for this public context come up from the 100% IBR system, but for the GB system it's slightly different. We probably always have some nuclear and some of the synchronous machine unit in running, so there's a need to maintain system frequency.
All right, probably let's do the last one and then I'll close up. How do you monitor minimum short circuit level and minimum inertia during real-time dispatch? And I guess, Anna, you talked
So I'll try
about
to attempt,
inertia, so let's talk about maybe a short circuit level.
So I think it's worth saying that it's very difficult to monitor. It's difficult to monitor short circuit levels in real time. So we currently don't do that. Any monitoring or any planning is done ahead of the control room timescales, or there's always a lag in the control room calculation. So that's how we look at the fault levels, even minimum or maximum fault levels. That's always the case. We don't have monitoring of real time maximum fault levels as well. So we have to, going forward, we have to think about what do we do in the control room timescales? Do we need to do something in control room timescales for minimum short circuit level, or whatever we are doing currently ahead of control room time is sufficient? So why do we need to do something different? So yeah, the answer is we don't currently monitor minimum short circuit levels in control room timescales.
All right, so we are about at the top of the hour, and I'm going to wrap up. I would like to once again thank National Grid ESO team for a very interesting presentation. I know you learned a lot during the presentation, and I learned a thing or two. As I mentioned earlier, an email will go out once the video file has been posted, and we'll get responses for your unanswered questions and post them as quickly as possible. We have just 3 questions left. We appreciate your engagement, and if you would like to stay engaged, I would invite you to participate in the next G-PST ESIG webinar on September 27th on update on changing role of resources and growth of utility scale storage. Further information of all ESIG webinars can be found on our website, www.esig.energy, under events, and you are all invited to attend. Information on G-PST webinars can be also found at www.globalpst.org. I would like to thank presenters once again, and also for taking time, and it's pretty late in GB right now, so thanks so much for that. We look forward to seeing you all again in the near future, and in the meantime, everyone take care, stay safe, and thanks again for participating. Bye now. Thank you.
Thank you. Bye-bye.
Thank you very much. Bye now.